Alright, 17A students, here are a couple examples of radioactive growth and decay. Actually, I'll start on the other side, sorry. So, exponential growth and decay. So, here's an example. A bacterial cell growth follows a model of dy dt equals 4 times y, where time is measured in hours. So again, this is saying the rate of change of y is 4 times the population y. So if I had, let's say, 300 cells, that would mean dy dt is growing at 1,200 cells per hour, which is a lot, right? So when the rate of growth is 4 times population size, right? I mean, it's a big deal. So, and we have an initial condition of y of 0 equals 150 cells. How long until there are 1,500 cells? So before we can answer this question, we really have to answer what the model looks like. So we're trying to get to how long time when y equals 1,500. Right, because y is the amount of stuff we have and t is time. So the solution of this differential equation, which Sanders talked about in class, is y, or y of t, equals c e to the 4 times t. And the reason that's true, so but whatever this coefficient here is going to end up as your multiple of t in the exponent. The reason this is true is because dy dt, if you take the derivative of this, you get c e to the 4t, right? The derivative of e to the 4t is e to the 4t times the derivative of 4t, which is 4. And this is just y, right? That's exactly what this is here. So this is equal to y times 4, or 4 times y. So that's why this is the solution. So whenever you're talking about exponential growth or decay, you're always going to have this model of c e to the something times t, where this coefficient of times t here is the coefficient that shows up in the differential equation. Okay. So we also know that y of 0 equals 150. So if we plug that in, we see that, okay, well, c is still c, we get e to the 4 times 0. So 150 equal to c times e to the 0 is just 1. So c, that constant, is 150. Okay, so typically, we always do what we just did to set up the model. So our model is y of t equals 150 e to the 4 times t. That tells us how much stuff we have at time t. And then we're asking how much do we have, or sorry, how long is it until we have 1,500 cells? So we're going to set y equal to 1,500, and we're going to solve for t. So let's see, y is 1,500, solve for t. 1,500 equals 150 e to the 4t. Divide by 150. Another way I could have phrased this question is how long does it take for the multiplication to multiply in size by a factor of 10? Right, because going from 150 to 1,500 is multiplying by 10. So then I'm going to take the natural log of both sides. Natural log of 10 equals 4t, and then divide by 4. Natural log of 10 divided by 4. We'll see. And I would leave my answer like that if I was just like doing work, but if I actually want to know what that is, let's see. Natural log of 10 divided by 4 is 0.57. So it's going to be 0.57 hours, which seems wrong, I gotta say. Did I make a mistake? Oh no, I did not make a mistake. Okay, no, that seems perfectly right. So, yeah, it takes a little bit more than half an hour for it to multiply in size by 10. Yeah. A way that people would also write this is this model is 150 times e to the 4th to the t. And so t, after 1 hour, this population would multiply by e to the 4th, which is a really big number. It's like 80 or something. So yeah, I can see this is totally right. Let's do this other example, which is kind of more typical of the kind of question I asked, but not what he did. A radioactive substance has a half-life of 40 days. If we start with 2,000 grams, how much will we have after 1 year? So we still have to find the model. So we know the model is y equals c e to the k t. And c is typically the starting amount, right? I like to make this little table where I have t, time, and the amount, y. At time equals 0, I have 2,000 grams. know 1 half-life later, which is 40 days later, I have half as much as I started with. And then asking how much I have after 365 days. So here's my model, which I'm going to replace C and K with what they're actually equal to. So C is 2000. We don't know what K is here. So in the previous problem, we knew K because we knew that dy dt was equal to 4 times y. Here we don't actually have that equation. So we have to solve for K. So plugging in this other piece of information, I know that y is 1000 when t is 40. Divided by 2000, 1000 divided by 2000 is 1 half. E to the 40k. Take the natural log of both sides. And then k is going to be the natural log of 1 half divided by 40. If you wanted to, although I don't think you need to, you could then go back and say, oh, the differential equation was dy dt equals this number, natural log of 1 half over 40 times y. It's kind of weird to do that, but whatever. And this number is negative because natural log of 1 half is negative, and it should be negative. We're talking about exponential decay. But I don't think we do that really. So then we want to know how much there is. So I should say, here's our model. Right, y is going to be c e to the k, which is what we just found. Natural log of 1 half over 40 times t. And if I wanted to find how much there was after 365 days, I just plug in 365. So you can plug in t equal to 365. And you would get y equal to 2000 e to the natural log of 1 half over 40 times 365. Which you can totally plug into a calculator. I'll do it in a second. But I want to also point out, as I saw Sanders do this thing where he said, oh, well, this thing here, you can actually simplify this. You can write the whole thing as 2000 times e to the, this is t over 40 times natural log of 1 half, but t over 40 times natural log of 1 half, you can write as the natural log of 1 half to the t over 40 power, where that's in the natural log there. But then the e to the natural log of some stuff, sorry, this is looking kind of wonky, I know. E to the natural log of some stuff is just that stuff. So this is really 2000 times 1 half to the t over 40. Which makes a lot of sense if you think about it, because it takes 40 days for half of it to disappear. And so if t is 40, you get 40 over 40, which is 1, and you get 1 half to the 1, which is 1 half, and 2000 times 1 half is going to give you 1000. So this is actually kind of, we could have totally actually started with this and be like, oh, I know it takes 40 days for half to go, so it's going to be 1 half to the t over 40. So then if I want to find this, you could also write it as 2000 times 1 half to the 365 over 40 and get whatever that is. Let's find out. Let's see. Either way, 1 half to the 365 divided by 40, just a little bit bigger than 9, is 0.00179, and then multiply that by 2000. And you get 3.58 grams approximately. So hopefully that helps with these exponential growth and decay problems a little bit.